define the linear transformation. That is transformation of x plus y equal to. And before that linear transformation, we must assuming the part of a linear mapping. That is T maps U to V or V to W, whatever it is. Because here U and V be any two vectors there. Then the vector space must goes to subspace condition, and just like that, the mapping is said to be a linear transformation. That is transformation of x plus y equal to transformation f x plus transformation of y. Okay, next one. Hello, can you hear me? Okay, so now that is a into transformation of x equal to A into transformation of x. Here A being the field element and x being the vector space. Okay, that is one of the important concept of linear transformation, and define linear transformation. Suppose in the final examination is given, one of the important the question is very important the theorem or problem is define linear transformation and give examples briefly. Okay, it will be just like that identity transformation or identity mapping is also a linear transformation. And the null mapping, identity mapping is I from V to B. That is one of the linear map. And now it is defined by I of alpha equal to alpha, I of x equal to x. Whatever it is, there are in the alphabetical letters, enter all the small letters taken as binary elements. At the same time, those binary elements are called objects or vectors, whatever it is. Outside of the elements, given outside of the space is called field of the elements. Now, those field elements are denoted by A and B, whatever it is there. Here, especially here, identity map is also defined from the map of identities. I maps B to P be defined by I of alpha equals to alpha or I of x equal to x. Now, that is the identity mapping. Null transformation is 0 of alpha equal to 0. Okay, that is the here A be any by x be any one of the vector is there. Here 0 of x equals to x, 0 of x plus y equal to 0 of x plus 0 of y, and the O of ax equals to a into O of x, because here O of x is represented by each and every element must be the 0. Now that's why it is called ideal null mapping is also 0 transformation. Null element is denoted by script book. That is the script O is the set of the null set. Okay. Even the set of all the elements are 0, that is called zero set. And according to the zero set means that is the zero element is there, and the two-step test are to verify the two-step test and the one-step test is there. Okay. Students listen carefully. And before that, the rank and nullity theorem it is completely based upon the linear transformation concept. Already we have in the previous class we have discussed some properties of linear transformation. Okay. Now the transformation of summation ai alpha I. So summation ai alpha I can be expressed as a1 alpha 1 plus a2 alpha 2 plus so on an alpha n. So transformation of a1 alpha 1 plus a2 alpha 2 plus so on an alpha n. So that is a1 into transformation of alpha 1 plus a2 into transformation of alpha 2 plus so on an into transformation of alpha n. So enter that is the linear combination of the transformation. A1 G of alpha 1 plus A T P of alpha 2 plus 1 A and T alpha n. These are all linear transformation. Okay. Now that is also one of the important in the final examination. And before that, what is the image of the element and image element or range of the element? And here the one of the transformation mapping linear mapping is defined by the linear transformation, that is T of T from U to B, any one of the linear that is called here U and V be any two vector spaces. Okay, U and V be any two vector spaces. Here U be the domain of this part and V be the range of the part. So that is the image of the part is there. Okay, here T of alpha, here alpha being any one of the vector given in the domain. T of alpha, here alpha belongs to U. So the domain of all the elements are linear transformation, the vector space, and T of alpha equals to beta. Here beta be the image of the element. That image of the element is denoted by it is based on the linear mapping T of alpha 1, T of alpha 2, and so on. Irrespective of the elements in the, that is the alpha values, alpha 1, we are taking the replacement of alpha by alpha I values. Here, I varies from, that is the index of this path, because I belongs to delta is there. Here, delta be an index of this set. Here, I equals to 1, 2, and so on, n. That is the, there are so many representations given in the index set. Okay. Now here, according to the image and the domain, that is the nullity, null space of the part. So according to the null space, you have to define the nullity of this part. At the same time, nullity element is also called kernel. Okay. Kernel already, the definition is also defined in the previous session, group theory and ring theory and etc. is there. That is the modern algebra. Especially this is the linear algebra through the dimensions. Null space of the dimension is called nullity. Students, listen carefully. Null space is denoted by here dimension of n of t. Okay, so that is a row of t's. Okay, here the row of t is called range of t or image of t. That is called rank of this part. Nullity is just like that. V of t is there. So that is the representation of V of t is called nullity. So dimension of null space is called nullity is there. Okay, NULLITY, that is the nullity of this part because they enter all the kernel elements represented as the zero. So that's why then the dimension of the given in the null space of the set that is called nullity is there. That is denoted by V of t. Okay, and at the same time, range space or image. Range space is denoted by R of t or image of t. That is IM of t is there. So all the range of the elements represented by so range space T of alpha 1 equals to beta 1, T of alpha 2 equals to beta 2, and so on. So enter all the range space of the number of images of the given the set, image of the elements given in the set, that is called dimension of range. So dimension of the range is denoted by dim R of t or dim image of t is called rank of t is there. So according to the definitions, rank and nullity, we must establish the one of the five finished theorem that is called rank and nullity theorem. Okay, listen carefully. That is you must please be careful and must watch. That is the sixth unit of this part, rank and nullity theorem, and it is completely based upon some problems are also going to practice here. Okay, students, this is the matrices session. Here, one of the that is please see and refer the unit 9 is there. That is the third unit of this block of third unit block 3. That is unit 9. What is the characteristic roots and characteristic vectors? And according to the establishment of this concept, Cayley-Hamilton theorem. That is one of the important theorem in matrices, especially. Okay, what is the characteristic equation? Before that, already we have learned in the previous classes under the lower classes, just like that in intermediate level or graduation level. Okay, what is the defined matrix and the types of matrices? And the zero matrix means that is also null matrix. Each and every element is zero. That is called null matrix is there. Now, just like that here, identity matrix is denoted by capital I. That is I2 equal to 1001. That is the 2 by 2 identity matrix is there. And what is the skew matrix? What is the Hermitian matrix? Okay. And these are all some types of matrices, especially what is the symmetric matrix? Okay, so what is the symmetric? A transpose equal to A. What is the transposition of the matrix is there? So, given the matrices, all the rows must be arranged. Interchanging of the rows and the columns given in the matrices, that is called transpose of a matrix. That is denoted by A power T or A dash, whatever it is. Okay, and according to the transpose of the matrix, we must establish the concept of here, especially because lambda be any one of the scalar AB and matrix. Square matrix of order is n by n is there, and according to the matrices theory, first of all, we will studying the concept of characteristic roots and characteristic vectors. And before the learning of the concept of characteristic roots and characteristic vectors, what is the characteristic equation? Now that is the beginning of this that is the fifth semester of this part of matrices is this is the block 3 and the equation. Here, just you have to see 9.2.1 is there. Just what is the definition of characteristic equation? Okay, characteristic equation. Here, let A be any one of the before that. Given the matrices must be a square matrix. Here, A be any one of the square matrix of order n by n is there. The number of rows and columns must be equal given the matrices, that is called a square matrix. So, and given the matrices is a square matrix. That is, let capital A be a square matrix of order n. N means n by n is there. Here, the number of columns and the number of rows and columns must be equal. That is called a square matrix. Okay. Here, let A equal to set of Aij. Here, n by n be any n row square matrices. Okay. And here, lambda be be a scalar and I be the identity matrix based on the given the matrix of because given matrix of the order is n. Suppose it also is there. What is the equation? That of this lambda equal to that's called that of means the determinant of the determinant of m is lambda equation. Characteristic root carefully students. Now the one of the important concepts is the characteristic equation that of a minus lambda equal to c, and you must mention the okay. Now there is the characteristic equation. Sometimes that is also called eigen equation or latent equation. That is the similar names, the replacing of characteristic of this part. Here, what is the characteristic equation? The characteristic equation means let capital A be in square matrix of order n, and IB and identity matrix depends upon the. Hello, please share the line. Screen share is not available here. Okay. Now just have to see this one. Characteristic equation of a matrix. Now here lambda represented as the characteristic root or eigen root or latent root or proper root is there. Okay. Now in the examination, find the characteristic roots of for the given the matrix capital A equal to given the matrices say either 2 by 2 matrix is also given or either 3 by 3 matrix is also given is there. Okay. Now next one. See this one. What is the characteristic of a equation of this part? How to define the determinant of a matrix? The replacing of characteristic equation. That of a minus lambda I equal to that is the data of a11 because you are given the matrices as on the linear homogeneous equation of this part. A11 x1 plus a12 x2 plus 1 a1 and xn equal to 0. That is the linear homogeneous linear equations. Already have practiced in the previous level to find the Cramer rule and through the given the linear equations, either homogeneous or non-homogeneous equations, to find the values of to find solve the equations. There are three equations are given, two equations are given. From those equations to find the unknown values representations. Okay, either x, y, z or whatever it is, alpha, beta, gamma, or x1, x2, x3, whatever it is there. Because here the number of equations is given here, n, m and m rows and n columns is there, because the matrix of the order is m by n. So now that is the n by n is given, and the replacing of given the coefficient matrix to find the characteristic of this part, that of a minus lambda equal to that of a11 minus lambda, because they enter the diagonal part replacing by in the a11, a22, and so on, a n. Replacing a11 minus lambda, we are taking the a11 minus lambda, a22 minus lambda, or so on, a n of minus lambda is there, and through that of a minus lambda I, because here capital A be the coefficient of a matrix, lambda be the scalar, and lambda be a scalar, and I be an identity matrix, depends upon the given the matrix of order n is there. Okay, now that is the characteristic equation is that of a minus lambda equal to 0. Okay, now how to characteristic vector means here a minus lambda I of x equal to 0, because here capital XPA, XP any variable matrix is there. That variable matrix is denoted by whatever it is. Here, what are the variables here? Constant matrix is entirely different the variable of a matrix, because those variables are represented as x1 or here x1 or a11 x1 or a12 x2, because x1 x2 so on xn. These values are called variable of a matrix that is denoted by capital X. Okay, here a minus lambda I of x equal to 0, that is called a characteristic vector of a matrix. Okay, in the and also after the simplification, we are getting the value ax equal to lambda x. Now, just you have to see and refer the one of the problem is there, that is 9.3.1. Just you have to see and refer into textbooks is the given the material already. You have to given the material through the university concept is that is 9.3.1. Just you have to see and refer the problem. Determine the characteristic roots of the matrix capital A equal to, because given the matrix are, then the order is 3 by 3. That is the first row is 1, 2, 3, and the second row is 0, minus 4, 2, and the third row is 0, 0, 7. Now that is the 3 by 3 matrix is given to find the characteristic roots and the characteristic roots of the matrix. First, and before that, give the to start the to solve the solution, given the problem, and before just you have to mention the we must mention the given the matrix capital A equal to 1, 2, 3, 0, minus 4, 2, and the third row is 0, 0, 7 is there. Okay, then the characteristic equation already. What is the characteristic equation? Please respond here, friends. What is the characteristic equation of a matrix? Yes, that of m is lambda equal to 0. Okay, now here the given the first of all, you have to mention the delta of A is given is there, minus lambda of I is also through the given the matrix 1 0 0 0 1 0 0 0 1. That is the 3 by 3 identity matrix is there. Replacing of depth of A minus lambda I equal to means that is in the diagonal elements 1 minus 4 7, and after the simplification we are getting that 1 minus lambda and minus 4 minus lambda and 7 minus lambda, the principal diagonal of this part. All the remaining elements are same, because 1 minus lambda, 2, 3, and the second row is 0, minus 4 minus lambda, and 2, and the third row is 0, 0, and 7 minus lambda equal to 0. Okay. Now here the after the simplification already we have practiced in the previous session, our previous classes is there, either intermediate level or UG level. Okay. So how to define the 3 by 3 identity, 3 by 3 matrix, how to find the determinant of this part. Determinant is denoted by det, det is there. Okay. Here, the first row of the first element, we are taking the through the row under through the first column to find the determinant of this part. Now, here, just here, through the row of this part, we are taking the first element, the first row of the first element is denoted by x11. So that is 1 minus lambda of and two options. Just you have to must ignore the first row and the first column, and remaining part of the determinant is minus 4 minus lambda of 7 minus lambda, because AD minus BC. Determinant of 2 by 2 Mahindra factor of the 2 is there, because 2 by 2 Mahindra factor here minus 4 minus lambda of 7 minus lambda equal to 0. After the simplification, we are getting here the to get the values of lambda. Those values are called lambda beta. Lambda is also called characteristic roots or characteristic vectors. characteristic roots or eigen roots or eigenvalues or characteristic values. Latent values or latent roots. Proper roots or proper values. They enter all the similar names here in the replacing of characteristic part. So once I have to repeat here, characteristic, latent, proper, eigen. There are similar names in the replacing of characteristic, either values or roots, whatever it is. Okay. Now we are getting the values lambda equal to 1 minus 4, 7 is there. First of all, at the lambda equal to 1, now characteristic roots and the practice here, we'll practice here, capital A equal to 6 minus 2, 2, and minus 2 minus 2.
This is
3 matrix is there. Okay. Now the 3 by 3 matrix, the 3 by 3 matrix, just you have to, we must find the characteristic roots. Okay. And corresponding characteristic of the matrix. The same also practice with the above problem is there. Just you have to see and refer the above problem and replacing the minus lambda equal second row of the second element is 3 lambda of the simplification of a minus lambda. So the principal diagonal elements are 6, 3, 3. Now replacing of a minus lambda is 6 minus lambda and 3 minus lambda and 3 minus lambda. Then to find the characteristic of the matrix, the characteristic of the equation. Okay, next one. Now, after the simplification of characteristic equation throughout the determinant of this part, that is lambda cube minus 12 lambda square plus 44 lambda minus 48 equal to 0. This is the third quadratic expression in terms of lambda is there. Here the third quadratic expression in terms of lambda. After the simplification, we are getting lambda equal to 2, 2, 8 is there. Now, students, this problem is very important in the final examination because one of the important problem, there are so many universities, this problem is given in the so many universities is there, okay? Either Usmania or whatever it is, Ambedkar University or other university. Okay, this problem is a number of times repeated here. Okay, the replacing of lambda equal to 2, 2, 8 is there, and at lambda equal to 2, you must find you will find the characteristic vector at lambda equal to 2. That is a minus lambda I. Replacing lambda equal to 2 is there because the first lambda 1 and lambda 2, those two vectors are same, and the third vector is entirely different the before of the first two eigen roots or eigen roots or characteristic roots or values, whatever it is. Okay. And the characteristic vector is a x equal to lambda x or a minus lambda I of x equal to 0 is there. And at lambda equal to 2, real lambda value is substituting given this expression, that is a minus 2 I of x equal to 0. Now, after the simplification, given in the above this part, that is if what is that? Just you have to see and refer this there. Lambda equal to 2. 6 minus 2. So that value is 4. And at the same time, 3 minus 2. That value is 1. Just you have to see the principal diagonal of the elements. And at the same time, 3 minus 2. That is also 1. That is the third row of the third element is there. Now, after the simplification, kept x equals to what is the x? That is the variable matrix. That is x1, small x1, x2, x3 is there. Okay, 0 is a null matrix. So we are taking the column 0, 0, 0 is there. Now, here to applying the row transformation or elementary transformation through the rows, and the first row and the second row must be interchanged so that elementary property, elementary transformation is denoted by R1 if and only if R2 is there, or R12, either R12 or R. There is also implication of the by implication of this part, replacing R1 by R2 and R2 by R1. That is the transparent of the first two rows. Okay. Now, second, we are taking the second row of the first part, and to write as the first row of part is as to you must be written as the second row. Okay. After the simplification, we are getting one of the equation is minus 2x1 plus x2 minus x3 equal to 0. Okay. Now there are three variables because all the this is the only one row is given because number of given the part is n minus r solutions. Here n be the given the matrix of the order. Matrix of the order is three, and here number of unknowns is n minus r be the rank of the matrix. So rank of the matrix is after the simplification characteristic vector, that is one is there. So n minus r solutions means 3 minus 1. There are two linearly independent solutions. That is the equation can be written as minus 2x1 plus x2 minus x3 equal to 0. So after the simplification we are getting here, suppose x1 equal to minus 1, remaining elements are 0 and 2 is there. That is x2 and x3. So here the capital x1 equal to first characteristic vector is denoted by capital x1. At lambda equal to 2, it is on the similar part, x to capital x2 equal to minus 1, 0, 2 is there. And x3 is also 1, 2, 0. Okay. Now, to find the characteristic vector through the characteristic values, because here characteristic values, first two values are same, that is entirely different from first two. That is the third one, lambda equal to 8 is there. At lambda equal to 8, to find the characteristic vector, that is a minus 8 I of x equal to 0. Now we are giving, now we must find out the characteristic vector is kept x equal to 1 to 0. Okay, that's enough. Now this is the concept of given this part in the exam in the final examination is given. Find the characteristic roots and the characteristic vectors for the given the matrix. Just like there are first two examples are well established problems. Second problem number of times thoroughly repeated the final examination. Okay, students listen carefully. This is one of the important theorem, that is Cayley-Hamilton theorem. Okay, in sometimes that is the short note as CH theorem is there. That is Cayley-Hamilton theorem. Cayley is one of the familiar mathematician in the matrix is there. Hamilton is also for founder of the matrix. Okay, in the name of Cayley is also the matrices to develop the matrices. That is one of the great mathematicians is Cayley. So that's why the theorem is called Cayley-Hamilton theorem is there. Okay, Cayley-Hamilton theorem represented as CH theorem. The examination final examination one of the important theorem in the final university examinations. So that is stated from Cayley-Hamilton theorem, and according to the Cayley-Hamilton theorem, to verify the Cayley-Hamilton theorem for the given the matrix, to verify the Cayley-Hamilton theorem to find the value of A inverse for the given the matrix. Okay. Next one. Here the first of all, see the Cayley-Hamilton theorem. What is the statement of Cayley-Hamilton theorem? Every square matrix satisfies its own characteristic equation. That is the statement of Cayley-Hamilton theorem. Every square matrix, because A being one of the square matrix, must satisfy the characteristic equation means that of A minus lambda equal to 0. According to the characteristic equation, to form a characteristic polynomial, that the characteristic polynomial must be equating to 0. That is called a characteristic equation, and that given the to find the characteristic equation must satisfying the for the given the matrix. Either to given the polynomial, either third degree polynomial or second degree polynomial, whatever it is. Okay, so that polynomial must satisfying for the given the matrix. Suppose see this proof. One of the important theorem is there. That is the Cayley-Hamilton theorem is there. Okay, see this one. What is the statement? Every square matrix satisfies its own characteristic equation. So the characteristic equation represented as that of A minus lambda equal to 0. Okay. Suppose given capital A is a square matrix of order n is there. That of A minus lambda I, that is the representation in the polynomial of this part, minus 1 whole power n of lambda power n plus a1 into lambda power n minus 1 plus a2 into lambda power n minus 2 plus so on plus an. That is the determinant of A minus that of A minus lambda I. Now, here we prove that the matrix equation replacing of lambda by capital X is there. Here xn. Okay, x power n plus a naught into x power n plus a1 into capital X power n minus 1 plus A2 into capital X power n minus 2 plus 1 plus an. Here an means an into I equal to 0. Now it is satisfied by giving the matrix capital A. So finally replacing capital X by capital A. So that is A power n plus A1 into capital A power n minus 1 plus A2 into capital A power n minus 2 plus 1 plus ANI. Here I be an identity matrix for the given the matrix of order n is there. Okay. So finally, now satisfying the equation of characteristic part is replacing x by capital A is there. A power n plus a1 into capital A power n minus 1 n1 plus a2 into small a2 into capital A power n minus 2 plus 1 plus an equal to 0. Because okay, see this proof. See the proof of Cayley Hamilton there. First of all, so you must write the given the elements of a minus lambda I. It is the utmost of the first degree in lambda is there. Those elements of adjoint of a minus lambda I, it is an ordinary polynomial in lambda of degree n minus 1 or less, because given the matrix of the order n is there, to find the adjoint because the adjoint of this part is decreasing for the given the matrix of order, so that is n minus 1 or less is there. So adjoint of a minus lambda I equal to, that is bn b naught into lambda power n minus 1 plus capital b1 into lambda power n minus 2 plus so on plus b n minus 1. Because given the matrix of order n is there, because then the after the adjoint then their degree is it is that is the less of the given the matrix of order n. So either given the matrix of order n, so that is either n minus 1 or n minus 2, whatever it is. And according to the adjoint of a minus lambda equal to b naught lambda for n minus 1, b1 lambda for n minus 2 plus 1 plus b n minus 2 of lambda plus bn minus 1. So all the b values are matrices in the type n by n, whose elements are functions of aij values. We know that after the multiplication and the above this part a minus lambda into adjoint of a minus lambda I. Already we know the concept is a into adjoint a equals to det of a into I is there. That is one of the established expression in the matrix algebra. Okay. Here a minus lambda I, because replacing of a by a minus lambda I and adjoint of a minus lambda I equal to the product of a minus lambda I and adjoint of a minus lambda I equal to that of a minus lambda I of I is there. Here a minus lambda I of replacing of the value adjoint of a minus lambda I equal to b naught lambda power n minus 1 plus b1 into lambda power n minus 2 plus so on b n minus 1. So after the simplification, we are getting the value minus 1 a minus lambda into adjoint of a minus lambda a value is an equivalent to that of a minus lambda I into I is there. That of a minus lambda I is minus 1 whole power n of lambda power n plus a1 into lambda power n minus 2 plus so on a minus lambda power n minus 1 plus 1 an of capital I. So please stay in the line. Okay. So after comparing on both sides, comparing the coefficients of like powers of lambda on both sides, okay, we get minus 1 into minus I into bn equal to minus 1 whole power n into I. So liking powers, comparing on liking powers on both sides, and AB naught lambda. This is the lambda nth degree of lambda value. Then their coefficient is minus I into bn equal to minus 1 into b naught equal to minus 1 whole power n into I. And second expression lambda power n minus 1 degree coefficient is AB naught minus IB1 equal to minus 1 whole power n into A1 of I. And last one, lambda power n minus 2 like powers must be equating on both sides. AB1 minus IB2 equal to minus 1 whole power n into A2 of I. So here lambda power n minus 1, lambda power n minus 2, and so on, lambda power 0. So here lambda anything power 0 is identity. So just like that, AB n minus 1 equal to minus 1 whole power n into n of I is there. Here A equal to C1, C2, and so on, C1, C2, so on, Cn. So then the order is 1 by n is there. Okay. After the pre-multiplying these successively by now replacing lambda by a is there. That is a power n and a power n minus 1 and so on, a naught, a power 0 and I are adding. These values are adding, we get after the in the left hand side of this part, enter the values are 0 equal to minus 1 whole power n, replacing by lambda by a. So that is a power n plus a1 into a power n minus 1 plus a2 into a power n minus 2 plus so on, a and I is there. So after the simplification, we are getting a finally characteristic equation in terms of capital A, that is a power n plus a1 into lambda, a1 into a1 into a power n minus 1 plus a2 into a power n minus 2 plus so on plus an of I equal to 0. Okay, this is one of the important theorem. So this theorem is given in the final examination. Now the type of giving the giving the question is straight and prove Cayley-Hamilton theorem, and to find the inverse of the for the giving of the matrix by using Cayley-Hamilton theorem. Okay, after the simplification, we are getting that of a minus lambda I equal to, because given this expression in terms of a power n is there. Okay, now to find the a inverse means that is a power minus 1. So that of a equal to minus 1 whole power n of an is a small an, all the coefficients of an value is not equal to 0, because given the when the that is not equal to 0, so given the matrix is a non-singular matrix, so then delta A equal to 0. Already here the expression is mod A into delta A equals to delta of A into I is there. Okay. Now to find the A inverse equal to, because A inverse means A power n minus 1, A power n minus 1 plus, because A inverse is also multiplying for the M characteristic equation, a power n into a inverse equals to a power n minus 1 plus a1 into a power n minus 1 into a inverse equal to capital A power n minus 2 plus 1 plus a n minus small a n minus 1 of I plus a n into a inverse equal to 0. Okay. Finally, we are getting a inverse equal to small a n into a inverse equal to enter the expression must be converting at right side. Now that is 1 by a n of a power n minus 1 plus a1 into a power n minus 2 plus so on plus a n minus 1 into I equal to 0. Okay. Okay. Now that is here that is the value of a inverse, and according to the characteristic equation, to find a cube a power 4 or a power, this year is 2024 is there. So for giving the matrix to find the a power 2024 is also the value is also to find the a power 2024 by using Cayley-Hamilton theorem. That is the one of the finest, the simplest concept theorem is there. That is the Cayley-Hamilton theorem, and according to this theorem, to find the a power 2021 or a power 2022 or a power 2024. Already in the basic classes or lower classes, just you have to find the given the matrix to find a square, a cube, a power 4, whatever it is. After the simplification, we are little bit power of the expression for the given the matrix, but it is a little bit more for the running of the year is also we are taking the running of the year for the given the matrix of the power, that is a power 2024, that expression by using the Cayley-Hamilton theorem expression. Okay. Now the basic concept is the characteristic equation. Okay. Finally, a inverse equal to 1 by a n of 1 by small a n of a power n minus 1 plus a1 into capital A power n minus 2 plus so on plus a n minus 1 of I equal to 0. Okay, students, listen carefully. Just we have to practice some other problems throughout this theorem. Okay, now this is the end of this part because only 10 minutes more for the end of this session. And also, now this is the last class of throughout the online. This is the last class of linear algebra. That is your fifth semester of mathematics. Because please listen carefully. Some other important questions is given, especially enter these this time of the concept. Okay. Now state and prove Cayley-Hamilton theorem. Listen carefully. Now this theorem is very most important in the final examination. And according to this theorem, to find the problem 9.4.2. Now all the values find the characteristic equation of the matrix. Capital A equal to but this is the 3 by 3 matrix is there 2 minus 1 1, and the second row is minus 1 2 minus 1, and the third row is 1 minus 1 2. Now and verify the Cayley-Hamilton theorem. Verify means every square. What is the statement of Cayley-Hamilton theorem? Students, please tell me. Now, here the statement of Cayley-Hamilton theorem is okay. Every square matrix satisfies its own characteristic equation. That is the statement of Cayley-Hamilton theorem. Okay. Now, here the delta of A minus lambda I equal to we are taking the principal diagonal of the principal diagonal for the given the matrix 2 minus lambda, 2 minus lambda, 2 minus lambda. After the simplification of A minus lambda I, and then to find the determinant of this part and to write the third degree polynomial in terms of lambda, prove the determinant of this part. Now, what is that? Here, finally, after simplification, we are getting the expression in terms of lambda minus lambda cube plus 6 lambda square minus 9 lambda plus 4. That is the expression of that is the polynomial expression through the delta of A minus lambda I. Okay, the characteristic equation of the matrix is after the simplification that is also multiplying it with minus. We are getting lambda cube minus 6 lambda square plus 9 lambda minus 4 equal to 0. The replacing of lambda by a, because that characteristic equation must satisfy for the given the matrix. Given the matrix in terms of capital A is there. So replacing of lambda by a equal to a cube minus 6a square plus 9a minus 4I equal to 0 is there. Now already given the matrix is given. Here the capital A equal to, and according to the A, to find the A square means A into A, and A cube is A square into A. Okay. Now after all the values to find the according to the polynomial A is given, and to find A square and A cube, those values are substituting in this polynomial. So that is after the simplification, A cube minus 6A square plus 9A equal to 4I is there. Now, by pre-multiplying of this part, A inverse is also multiplying given this polynomial. To find the A inverse is also easy to find out the A inverse. Okay, after all the values is substituting given in this polynomial to verify, and there almost all the expression must be equal to 0. So that is the square matrix satisfies its own characteristic equation. This problem is very important in the final examination. Students don't understand here. Okay, listen carefully. To practice some other problems through the example, through this one. Okay. Okay. Now, some other important questions is also, please don't note down. Define an inner product space. Please note down. Define an inner product space, because the remaining units are also. Please ignore the classes, because this is the last session of the of online classes. Okay, please note down here. We have some other important questions and theorems or problems. Whatever it is given, this is the final version of end of this session. Okay, define an inner product space. Define an inner product space. New examples. And the next one, define Euclidean space. Define Euclidean space and a unitary space. Define Euclidean space and a unitary space. Already we have discussed the Euclidean space and the unitary space. The field of the elements, because the field of the elements are real numbers, that is called Euclidean space or real inner product space. Even in the inner product space, all the field of the elements are real numbers. Suppose in XB and inner product space, even the field of the elements means capital F equal to R. That is called a real inner product space or a Euclidean space. Suppose given the field of the elements are complex numbers, that inner product space is called a unitary space or complex inner product space. Okay, define inner product space, give example, and one of the finest theorem and inner product space. State and prove, state and prove Cauchy squarge inequality. State and prove Cauchy squarge inequality. That of inner product x and y equal to norm x into norm y, or inner product of x and x and the inner product of y and y. Inner product that of inner product of x and y equal to norm x and norm y. So here, what is the norm? Double mod norm is square root of x square, because here x being the vector space of the element. Okay, define a norm and a normalizer. Define a norm and a normalizer. Okay, define a Euclidean space and a unitary space. These are all very important definitions in an inner product space. State and prove triangle inequality. State and prove triangle inequality. State and prove Bessel inequality. State and prove polarization, parallelogram law. State and prove parallelogram law. Parallelogram law. So, now these are all very most important properties in an inner product space. Okay, inner product space is denoted by the depth of double mod of the part the lies between the vector space elements lies between less than and greater than. Depth of inner product of alpha and beta, or depth of inner product x and y. Okay, that is the simplest expression in inner product space. Okay. Now, these are all very important. The concept of inner product space, that is the definition. See the definition and the example, and just like that, according to the vector space definition and the inner product space definition, what is the Euclidean space? Okay, and a unit space. Okay, some other inequalities are there: triangle inequality, Bessel inequality, and parallelogram law. A parallelogram law. And one of the important term is Gram-Smith orthogonalization process, GSOP. Gram-Smith orthogonalization process. And before that, what is the orthogonal and orthonormal vectors? Orthogonal means any two vectors in their inner product space, in any two vectors, or we just have to take in any two vectors, then their inner product must be equating to zero. That is called orthogonal. Suppose x and y be any two vectors. Here x is perpendicular to y. That is the representation of orthogonal. Is x perpendicular to y, or inner product of in x and y equal to zero. Okay, so that is called orthogonal. Orthonormal means that is the Kronecker delta. Here, inner product of xi and xj equal to 0. If I not equal to j, suppose if I equal to j, that value is 1 is there. Here, that expression is called orthonormal. Okay, here represent vector is a capital X P any one of the vector, and orthonormal is denoted by x by x divided by double mod of x. That is called y1. So here y1, y2, y3, these are all orthonormal vectors through the definition of orthogonal vector. Okay, orthogonal means inner product of xi and xj equal to 0. Okay, that's enough. Okay, students, this is one of the important concept in an inner product space. Now, this is the last class. If you have any doubt, please contact us and personally throughout my WhatsApp number. Please note down my WhatsApp number is 9989 476833. 9989 476833. This is my WhatsApp number. If you have any doubt, please contact us and personally. And some other important theorems, we will discuss some other important theorems throughout the WhatsApp group is there. Because this is the end of the session, and this is the last class through the online part. Okay. Okay. Thank you. Once again, thank you. Wish you all the best and all the best to one and all. Please respond. Are any doubts? Okay. Thank you, one and all. Wish you all the best and wish you good luck.
Family with the book.
Correct.